Okay, we are officially on our next unit, so you should have created a new blog page called Earth's History. We are going to talk about fossils, the geological time scale, and relative and absolute dating within this chapter. There's not a whole lot of notes. We do a lot of projects that will give you a lot of information, and you'll have to find a lot of information on your own for this unit. But there are some notes to give you a rough outline of the major ideas behind this unit. So let's start with uniformitarianism. That is quite a mouthful. I will say it again. It is called uniformitarianism, and it states that geological processes that happened in the past can be explained by current geological processes, which basically means that what happened in the past is going to be explained by what happens now. Geological changes just means changes that have happened to the Earth. Geological is the study of Earth and rocks and history of Earth. And so it's basically going to explain what happened in the past based on what's happening now. You do need to know that Earth is roughly 4.6 billion years old, and geological processes generally happen at a slow rate. They're not as rapid they don't rapidly change as often as they do gradually over time. They're going to slowly change. Weathering and erosion and deposition are very slow processes that happen gradually, a little at a time. All right, there are 5 key ways to preserve a fossil, or to create a fossil, basically. You can get it trapped in amber, which is a tree sap. It looks yellow in color. What happens is the sap starts as like a sticky substance. It traps the organism that's going to be created as a fossil, and then that organism and that sap will harden and it will create a fossil. Those are pretty cool. Trapped in asphalt. Asphalt is a black tar. There's tar pits in different parts of the world. These tar pits are very similar substances as amber, as in that it's sticky and it's liquidy, and then it hardens and it will become asphalt. So a organism can get stuck in a tar pit and then eventually harden to create a asphalt fossil. Buried in rock, it can get trapped into rock layers. Fossils are only found in sedimentary rock because sedimentary rock comes down in layers. And when they're creating those layers, sometimes it will trap organisms within those layers to create a buried in rock fossil. Frozen. You can get frozen into ice to create a fossil. A great example of this that you guys have already talked about in English class is Ötzi. Ötzi was a frozen fossil. The body was frozen, which preserved the remains. Petrification is probably the hardest one to understand. Petrification is, most commonly petrification happens with wood. And petrification happens when an organism's tissues are replaced by minerals. So instead of it being the organism's tissue, it's actually just minerals, so it looks different. Like I said, a petrified piece of wood is definitely going to be your most common. Bones can get filled up with minerals. They can kind of they lose that bone hard tissue to kind of create a cast, and then it will get filled in by minerals to create a mold fossil, which is all part of the petrification process. Here's some pictures. You don't have to put any pictures on your blog. I just want to show you some cool pictures. This is actually a gecko trapped in amber. Notice that it is hardened over time. It's no longer a sticky, liquidy substance, but it was trapped and preserved. This is a fossil buried in rock. This is a fossil trapped in asphalt, some sort of beetle. This is petrified wood. So notice that right here in the middle, instead of it looking like wood, the wood has been replaced with minerals, and that's that petrification process. And here is a really, really cool, huge frozen fossil, which looks like a mammoth, pretty awesome fossil. They get frozen and they die, and they get preserved into the ice until the ice would melt. And then if the ice melts, then they're no longer preserved or trapped in that ice. All right, so let's talk about what a fossil is. A fossil is a trace or remains of an organism that lived long ago. And like I had originally said, they're most commonly preserved in sedimentary rock. You're not going to see fossils in igneous or metamorphic rock. And you're probably wondering why. Well, what we're going to learn in the next unit is how the rock cycle happens and how a rock will go from sedimentary to igneous to metamorphic. And basically, the conditions that create a metamorphic and igneous rock are too extreme in temperature to actually preserve a fossil. It generally will kill any remnants of any kind of organism, so it won't actually keep a fossil. Whereas the sedimentary rock, it goes down in layers, and then an organism can easily get trapped within those layers, and then it's preserved as a fossil. But igneous and metamorphic, the temperatures are so extreme, the pressure is so extreme that the organism, no remnants of it survive to create a fossil. That's why it's going to be found in sedimentary rock. Now, fossils can tell us two major things. They can tell us how the environment has changed over time, and they can also tell us how life forms have changed over time, or adaptations of life forms. Just simple things. If you have a fossil from several centuries ago and you have a fossil current day, you can compare the two organisms to see if there was any adaptations that they had to make to survive life. Scientists use 3 different things to understand how climate changes over time for Earth's history. Ice cores are big chunks of ice they pull out, and they see how thick the ice is in certain sections. The thicker the ice, the more rainfall you had. The thinner the ice, the less rainfall you had. These are called bands, and band size will show you how much precipitation fell during that year. So those are pretty cool. The ice cores can tell you a lot about what the amount of precipitation we've had in the past, which plays into our climate, how hot or how cold it is. Tree rings act very similarly to ice cores. Tree rings tell you how much water you had over a year. If a tree ring is thick, it means the tree grew really well, which means that there was plenty of rain and favorable temperatures. If the tree rings are very, very skinny or small, that means that the temperature conditions were poor and there wasn't much rainfall, depending on how well the tree was able to grow. And then finally, seafloor sediment. Scientists can cut out a chunk of the seafloor and do essentially the same thing they do with the tree and the ice. They're going to look at what organisms are trapped in there to determine what kind of conditions they were in. If it's too cold, certain organisms can't survive. If it's too warm, certain organisms can't survive. So they look at what kind of fossils they see, and they try to date back and figure out what the climate looked like at that time. All right, there's 2 types of dating we're going to talk about: relative dating and absolute dating. Now, the big difference that I want you to understand about relative versus absolute dating. Relative dating happens in a general sense. You're talking about it's about this old, whereas absolute dating is going to give you an exact answer of how old something is. So relative is exactly as it says. It is relative. And absolute is exactly as it says. It is absolutely that time. Absolute dating is a lot more difficult to understand, and we just kind of scrape the top of absolute dating in this grade level because it is very complex. It gets into radioactive decay and isotopes and things that we haven't talked about yet and we're not ready for yet at a 6th grade level. So we will talk briefly about absolute dating, but we're going to talk a lot more about relative dating because it's something that we can study the rock layers and figure out. So the definition of relative dating is to determine whether an object or event is older or younger than another object or event. And there's a couple laws that help us with relative dating. The law of superposition is the first one. And old rocks are on the bottom and young rocks are on the top if they're not disturbed. Very easy to understand. Old's on the bottom, young's on the top. Law of cross-cutting says that if any disturbance in a rock layer is younger than the layer it cuts through. So you're never going to have, not that you never have, but most likely you're not going to have perfect rock layers. There's going to be some sort of disturbance that happens. And we're going to talk about what those disturbances could be. When those disturbances happen, you have to remember that the disturbance is going to be younger than the layer it cuts through, because that layer had to be there first before it was able to disturb the layer. So let's talk about these different disturbances. Folding is one disturbance that can happen to a rock, and this is a real picture of rock, which is pretty awesome. And you can see how it folds. How it quite literally folds the rock. And folding is the bending of rocks that can happen when rocks are squeezed together. So they're squeezed together, it got a lot of pressure, a lot of heat, and then it was able to fold the layers of the rock. So this is called folding, which is a disturbance. Tilting is what happens when Earth's forces move the rock layers up and down unevenly, and then they create a tilt. You can see that these rock layers are tilted, which is pretty nifty. A fault is a break or crack in Earth's crust where rocks can move. So you can see this nice line right here through the rocks, and that is a fault that occurred, or a crack in the Earth's crust. An intrusion is igneous rock that forms when magma is injected into the rock and then cools and becomes hardened. So right here is where your igneous rock was once magma, and it was liquid magma, molten rock, and then it hardened, and when it hardened, it created a rock, and now you have that rock right here. And magma that hardens is igneous rock. So you have your sedimentary rock that's layered, and then you have your magma that comes in as a liquid, scorches through here really hot, and then hardens and creates what's called an intrusion. A uniformity is a missing layer of rock when rock is eroded or when sediment is not deposited for a long period of time. You can tell in this picture there's a drastic change in the rock layers here. This one is a pinkish color, reddish, and then there's an abrupt line. And then there is the new rock layer. Now that layer could have been eroded and weathered and disappeared, or it could have just been that there was no sediment deposited for a period of time, and so then it made the rock layers look like there was a missing layer. So uniformities is known as a missing layer of rock. All right, let's touch on absolute dating. Absolute dating is to determine the actual age of an event or object in years. Again, I want to touch on the difference between relative and absolute dating. Relative dating is a roundabout time comparing when something happened in relation to others, but absolute dating is going to give you an actual age of the event or object in years. So it's going to be a lot more accurate, but it's also a lot more difficult to find because it's more accurate. So keep that in mind. All right, our last chapter in this unit is going to be about the geological time scale. And you guys will talk about different geological time scales, and we will do a newspaper project where you guys will each create a newspaper from your geological time span. But you first need to understand how the geological time scale works. And it's divided into intervals, and these intervals are based on major events that occurred or changes that happened on Earth that outline these different intervals. Now, the largest interval is an eon. Okay, we have our geological time scale broken into 4 major eons, which is the Hadean eon, the Archean eon, the Proterozoic eon, and the Paleozoic eon. Those are the largest intervals of times. Within eons, there are eras. We have 3 main eras: the Paleozoic era, the Mesozoic era, and the Cenozoic era. So those are the 3 eras, I'm sorry, I was saying eras, my bad, that we have mapped out in our time scale. Then you have periods of time, like the Jurassic period or the Cretaceous period, which is going to be a smaller amount of time than an era or an eon. And then finally you have epochs, and epochs are the smallest time period intervals. Okay, and there's a great timeline on page 122 and 123 in your textbooks that shows you these intervals of time and some major things that happened. The most common thing that people know about the geological time scale is the time of the dinosaurs, which happened in the Paleozoic eon in the Mesozoic era. Which is really more in the Jurassic and Cretaceous period. So it was in the Paleozoic eon, which we're currently still in the Mesozoic era, and in the Cretaceous period or the Jurassic period. Dinosaurs were beginning in the Jurassic, and they really hit their prime during the Cretaceous period. So those are probably the most common things you know about. Life was sparse. It didn't begin until the Paleozoic era. And it began to flourish in the oceans first, and then it started to get broader and broader, and more life forms were created. So that's all the notes we have for this chapter. Make sure you have them on your blog page and saved in an organized fashion, please. And then that's all you have to do for your notes. Thanks for watching.